All right, good afternoon, everyone. Thank you for coming to this talk, which is basically clickbait, and a talk that's mostly going to be about Java at a Kotlin conference. Java got its start a really long time ago, especially compared to Kotlin. And in terms of language features, it actually didn't evolve any until Java 5, which was nearly 8 years later. And this is when generics came in. Can you imagine programming in a language without generics for 8 years? I guess you can ask people at Go conferences what they feel of that. But then the language, after this 8-year gap, there were no new language features, but after this, they started to trickle in more. And so 7 years later, Java 7 got things like switches on strings, try with resources, and then some type inference and like the diamond operator. This is actually the same month that Kotlin was first announced, having been in development for about a year at that time. And then 3 years later, but with probably being in the works for almost a decade, we got lambdas, which was pretty much the largest change to come to the Java language, and certainly one that modernized it and made it tolerable. So 3.5 years after Java 8 came Java 9, and this was actually 18 months late. So it was meant to only be about 2 years after Java 8 that this came out. It was explicitly delayed twice. And this came with like the module system. And what really came out of this, though, is the release process change to Java. And so after Java 9, which was September of 2017, Java 10 was released just 6 months later. And then this cadence kept up every 6 months. So Java 11, Java 12, and now to where we are today, Java 13. I feel like a lot of people might not realize that Java is all the way at version 13. You hear people just talking about Java 8 as if it's sort of the latest thing, or maybe they know about Java 11, but this cadence doesn't stop. And so the title of this talk refers to Java 19. And so we can sort of project into the future when that's going to be. So in another year, we'll have Java 15 being out. One more year, Java 17, and then Java 19. It's really not that far away. It's only 3 years. So what we're going to do for this talk is focus on this point in time, 3 years in the future of Java, and compare it to the language features that we know and love in Kotlin. There's in-progress Java enhancement proposals that you can look at. There's talks from people like Brian Getz, who work at Oracle, who talk about where the language is going and what we can expect to see. And there's even branches in versions of the JDK that you can download, compile, and build and use these language features that won't be there for another couple years. All right, so this is where we're going to be. We're going to be at KotlinConf 3 years in the future, and we're going to ask ourselves the question as to whether Kotlin is still going to be relevant because of these language features that Java is going to get. Another thing I want to point out before we start is this is only covering language features of Java. So in that time, there will also be new APIs. There will also be enhancements to the virtual machine to make it faster. We're not going to talk about those because you can use those in Kotlin, assuming that you're targeting the JVM and you have the ability to update to Java 19. You'll be able to use those APIs on day one. You'll get those virtual machine improvements for free. So we're only focusing really on the language itself. All right, I'm going to start with a little warm-up. This is not a feature that's in Java 19. This is actually a feature that's already released in Java today. But I want to show you the structure, the format of how these comparisons are going to take place. So in the Kotlin that we love, we can do things like this. We can declare a variable or a local property without its type. And so it's going to be inferred that it's an integer. As of Java 10, you could do the same thing. You'll notice that they don't have val, they have var. And the reason for that is Kotlin is able to distinguish between read-only values and read-write values. But in Java, since they already have conventions for this, and for another reason we'll see in a second, they opted to keep the additional final modifier for you to create a read-only value. You'll notice I say read-only, not immutable, because these are actually both in the users. These are actual mutable lists. So it's really that we just can't change the reference to the list, not the actual type itself, or like the values in the type. In Kotlin, the type is syntactically separate from the val var declaration. But in Java, var is just a replacement for the type. And so if you need to specify the type for any reason, such as null, which you can't be inferred to a type in Java, you have to get rid of that nice var, that shorter var syntax. And this is also like in Kotlin, you can also use this to narrow the type that a property is. So if this was like a public val, the tasks, we wouldn't want to expose the implementation of ArrayDec. We would only want to expose dec to our users. And so that's just the same as Java has been doing. Another interesting way that type inference sort of plays with features of the language is lambdas. So in Kotlin, we can declare a lambda in a property, but we don't have, as long as the type can be inferred from that lambda, you don't have to actually declare it. Unfortunately, in Java, if you do the same thing, this is not going to work because in Java, lambda types are associated with actual types. And so it doesn't know that this type matches runnable because there might be 100 interfaces that have a single method that just have a void. We're not specifying anything, and so you can't actually do this with var. If you're doing a lambda, you always have to go back to anonymous inner classes. A nice property of what Kotlin did here is that you'll notice the names of the variables all line up. Whereas in Java, if you're trying to scan down those locals, the names are kind of indented and all over the place. And so, even though we're comparing these as the same thing, in Kotlin, val and var have nothing to do with type inference. They're just ways that you declare properties, whereas in Java, var is actually a replacement for a type. And it can only be used on locals, and in Kotlin, we can use val and var for declaring properties on classes and such. All right, so that's a taste. That was Java 10. Now we're going to start moving into things that aren't here yet. All right, so this is a function that recursively walks a graph of nodes and tries to find if any node matches. And so what this does is it actually declares the function inside the function that you would call to perform this recursive operation. And this doesn't need to be public, and it's not used by any other function, so we can declare it to be private to this one. You could do some cool things, like it captures the hash set from the enclosing method function body and uses it. It also captures the predicate argument that's coming in. And then it recursively calls itself on a different node. So this is actually doing quite a bit. Java is actually getting this feature, and this is probably what it's going to look like. It's currently under experimentation in something called Project Amber in the JDK, and that's actually where most of these things are going to be. And so hopefully it'll be in preview in probably Java 15 or 16, which is about a year, and then stable a year after that. If we look in the bytecode as to what this turns into, you don't really need to know much about bytecode. I'll kind of go through, but it's interesting to note that what happens here is Java just takes that nested method and hoists it to a sibling static method that is in the bytecode. And so when our outer function, our outer method calls that, it just turns into a static invocation of this private function with a goofy name. And you'll see its arguments are actually the things that were captured as well. That's how Java does it. If we go back to the Kotlin example, and we take a look at how it gets compiled, what it gets compiled into, it's a little bit different. What's happening here is it's actually allocating an object and then passing those two captured things, the set and the predicate function, into its constructor. And then later on, it's calling a virtual method, which is like an instance method, on that object. And that's because this basically is done using how lambdas work. So they take nested functions and sort of fake them into lambdas. And so we get a class generated for every nested function. It has the type signature of a lambda. The things that it was capturing are passed in as arguments and how it is fields. And then the function is just an instance function on that object. So it's a little less efficient, especially if you're on something like Android where class counts and method counts matter. There's actually a bug tracking doing something similar to what Java is doing. So hopefully this can be improved in the future. And the nice thing is that it can be improved and you'd never even know. And then actually, if you're an Android user, like R8 should be able to eliminate that allocation, and it currently trips up a little bit, so there's a bug that will hopefully eliminate those classes as well if you use R8. But in terms of just the language feature, like there's no clear winner here, right? Like Java is just basically getting the exact same feature as Kotlin is getting, and hopefully by the time it ships in Java, Kotlin will have its new IR backend where it's much more easy to specialize these language features, and it will be equally as optimal in the bytecode. Multiline strings, fantastic feature of Kotlin. What this ends up producing is, can you see that? Oh, yeah. If we don't do anything with a multi-line string and it happens to be indented, that indentation is going to be retained. But thankfully, because of other features of Kotlin, like extension functions, we have library functions that can sort of mess with the indentation. So you might be familiar with trim margin, where we put these little pipes in a row, and that allows us to eliminate the indentation while sort of retaining the indentation in the source code, so that as you're scanning down, like a multi-line string is not slammed to the left of your source file. Some cool features of trim margin you might not know. You can actually specify a custom margin, like delimiter. I guess if you happen to have a multi-line string that is using pipes as its very first character, you would want to do something like this. And then there's also trim indent, which doesn't require pipes. It just takes the common string prefix from each line and removes it. Both trim indent and trim margin can actually be computed at compile time. So you're in the bytecode, that string already has had the indentation removed as long as it's also a constant. So multi-line strings are something that was introduced experimentally in Java 13, which is the current release that's out, and will also be experimental in 14, but hopefully stable in 15 or 16, which is sometime next year. The way that it works is it behaves like trim indent is always going to be applied, and so you don't have to do anything with this. It's going to find the common prefix of whitespace and automatically remove that. It has some other cool features that Kotlin really doesn't have an analogous for. If you're doing a multi-line string, but you actually want the final string to be a single string, there's a new escape sequence, which is like just the slash and nothing after it, which will actually remove that new line. Oh, I missed let me go back. So if you're using this in IntelliJ, I was wondering why I didn't see anything. There's this little line that shows up. It's like a guide to show you where the indent will be removed. And it only does this for Java multi-line strings, not Kotlin multi-line strings, which I thought was a little weird. I meant to file a bug for that, but I didn't get around to it. But that's like a cool little feature of IntelliJ that visually shows you what is going to happen to the string while you're in the editor. OK, another interesting example of what Java does compared to Kotlin. This is a test case from a library that I worked on, and it has significant trailing white space. So the last two lines of this multi-line string have four spaces and 2 spaces, respectively, that need to be there. If I port this test case back to Java, what's actually going to happen is those trailing white space are going to be removed automatically. This is another case where they've had to sort of invent something new, where they added a escape sequence for space. And so these \s's will just turn out to be spaces, and then that means the spaces that precede them will also be retained. One aspect of all Kotlin strings, but especially useful in multi-line strings, is string interpolation. This is where we can reference reference any property that we can get access to inside the string itself, and Kotlin will perform the replacement. This actually turns into a bunch of string builder code. So it's like concatenating a bunch of things in a string builder on your behalf, and then calling toString on it. But this prevents that optimization I talked about before, which was computing the indent at compile time. And so you see we wind up with a call to actually perform the trim indent at runtime. So if we were to make a direct equivalent to this in Java, we would have to do string concatenation, manually. Obviously, a little unfortunate in terms of like the syntax and the source that we have to write, but there's actually a really interesting property of what happens in the bytecode if you do this. If you look, when this is compiled, we don't see a string builder. We don't see a bunch of appends. It has this thing called invoke dynamic, and it calls this crazy long method, this thing called a bootstrap method. But if you look at what it's called, it's string concat factory, make concat with constants. And what this is going to do is at runtime, the first time it's called, it's going to dynamically generate that string builder code. But it's going to do it in a very intelligent way where it checks every single argument that you're passing in. So we were passing in 3 properties before, the name, a name. It's going to check the length of those names, check the lengths of the constant portions, and it will size the string builder exactly for how much space is needed. So when you run this, it's going to be essentially it's going to pre-allocate a character array for exactly the amount that it's needed each time the name, even if the name changes. But like I said, this is the equivalent to what we would write in Kotlin, but it's not multi-line strings. So what if we want to do like a multi-line string and replacement? So what they've done is they've actually added a method to the string class, which is string.format, but instead of being a static, it's now an instance method called formatted. And so you can sort of have a better experience than having to put string.format at the beginning, which is always a pain because you write top to bottom and get the formatting for you. And so you might think that this loses that performance optimization of the invoke dynamic and generating things dynamically. But that's not actually true because this new format method that comes with the multi-line string language feature also comes with a version of invoke dynamic that knows how to do that same trick where it pre-sizes things and gets everything ready so that you never the string builder never has to expand and it never over allocates. And so there's a new method coming with that feature where the formatter can actually do its work and produce this code at runtime. Again, this is part of that Project Amber, and will probably ship in the Java 15 or 16 timeframe. In terms of the language feature, Kotlin definitely wins with string interpolation, but Java's not that far off, right? Especially if you're not doing string interpolation, you just want the multi-line string feature. It's certainly, I don't think it's clear whether or not the automatic trim indenting is going to be something that users like or users hate. I guess we'll have to see over time. But multi-line strings is something that's been sorely missed from Java, especially if you're doing things like database queries. And there is a Kotlin issue for using that string concat factory. So that's only available on Java 9 or higher. But if your Kotlin compiler, if you tell it that you're targeting 9 or higher, it would be great to see Kotlin emit that bytecode. OK, so data classes are the thing that shows up on just about every intro to Kotlin's blog or talk, because it's great showing like a 150-line Java file of a POJO getting turned into 1 line of Kotlin. However, in about a year and a half, those blog posts are probably no longer going to exist, because Java's getting this thing called records, which is essentially their equivalent of what a data class is doing. It's actually going to be available in preview in March in Java 14, and it'll probably stay in preview for 15 and then stable in Java 16. If we look at the bytecode signatures of what this produces, they're very similar. Both produce a final class by default. One difference is that in Java, they actually extend a base class. Right now, this record type, it just re-declares toString equals and hash code as being abstract to essentially force you to re-implement them in any subclass. A really interesting thing is currently, Java has abandoned the getter prefix for accessing the values that are in a record. Whereas in Kotlin, it retains that prefix and converts your name and your age to get name and get age. So it'd be really interesting for the interop story. So if you're consuming a Java library that's using records, it's not going to have methods that have get prefixed names, and so Kotlin is not going to turn those into properties. I assume what will happen is they'll look for something that extends record and then just take any method that returns a value and turn those into properties. But it's certainly going to have interesting implications for interop, and it'll be interesting to see what Kotlin does as a result. Both have equals hashcode and toString. If we look at the implementations of these toString methods, we see something we've seen before. Kotlin just generates string builder code where it puts a little person prefix and then concatenates your properties and then a little curly brace at the end. Java, however, is relying on invoke dynamic again, where it doesn't produce code for these equals hashcodes and toStrings. One, because you might not be using them. You might never put this value in a map, so equals in hashcode, or never call it. Or you might never call toString, because in production you're not logging. You don't have like debug logging. What's interesting about the Java invoke dynamic here is that it's using a new method, this object methods bootstrap. And what's happening is that this is used by all three of these methods. So hashcode and equals, they all call into this same new class. It's a pretty clever trick to reduce bytecode size. I assume it improves like startup time because the verifier doesn't have to like parse all these bytecodes and stuff. You might see that I omitted the copy method and the component methods of the Kotlin version. We're going to talk about component methods later on, but the copy method is something that Java has no analogous to. And so from a language perspective, there's really not much different here except for that copy method, and so that sort of gives Kotlin the edge. But in terms of runtime performance, the Java version is going to be, in theory, better because of its use of invoke dynamic. So one thing Kotlin could do today is if you're targeting Java 9 again, that toString could use string concat factory instead of all that string builder. But it can't. The objects methods class that the Java is using, that's not going to be available until this feature ships in Java 16 or whatever. And then if you're targeting Java 16 from your Kotlin, then the compiler could potentially use it. All right, Kotlin sealed hierarchies allow us to limit the number of subclasses of a particular type. And so our person example that we've been using, we might want to seal that in, say, a developer hierarchy where this is like the developer of an app. It can either be an individual or it could be a business. In Java, we'll be able to actually do the exact same thing. The syntax is almost the exact same as well. This should be in preview in Java 15 or 16, and then stable in 16 or 17. And I'm using data classes and records for these examples, but this language feature works with regular classes in both languages. It's obviously just shorter on slides to use these more efficient representations. A cool thing about Java that Kotlin cannot do is that it can actually seal interface hierarchies. We'll see how that works in bytecode in a second. And then you can do all the things you might expect, which is like declaring abstract members on the sealed class. In Java, you'll be able to do that as well. And you'll notice that I don't have to stop using this shorter constructor notation of the record. I can do things like put annotations right on the properties there. OK, if we look at the bytecode signatures with the Java P tool, we can see the differences in how sealing is implemented. So both have their properties declared on the base type. But then the mechanisms by which sealing occurs is very different. Kotlin requires you to use a class for sealing. And that's because what they do is they actually make the constructor private so that anyone consuming your library or whatever is never able to subclass it and call the superclass constructor. But obviously there are the subclasses that you wrote, and those need to call some superclass constructor. And so they actually insert a synthetic constructor, and synthetic means that you can't see it from source code. So even though this is public, a Java developer would not be able to call this method, or in a consuming Kotlin from another like module or whatever, you also wouldn't see this method. But the Java version, I mean, it looks like I just kind of wrote that there. These are called attributes. They exist in the bytecode file. They're like associated with the class. And so this interface has the attribute permitted subtypes, and those declare the types that are allowed to be instantiated of this type. Once again, like Kotlin might be able to use this feature. Once this becomes stable in Java, Kotlin might be able to move over to using this permitted subtypes feature if you're targeting Java 17 or whatever and higher. And that would potentially allow Kotlin to start sealing interfaces as well. So once again, these are extremely similar, and if anything, Java gets the edge here because of its ability to seal interfaces. Okay, if we're receiving things of a certain type and we need to do a type test to check if it's another type, we can do that in Kotlin using is. And what's pretty cool is that the language has this thing called Smartcast, where anytime I use that variable, that local property that I did the type test on, inside the block of the type test, so in this case an if, the type is automatically known to be what I checked for, and so I can just use it as an integer, and in this case perform a mathematical operation with it. Java is getting a similar feature, a feature that you can perform the same use cases with, but its syntax is slightly different. As you can see here, we actually have to specify a second, like a new name for the thing, and only that new name, in this case I, will be of that specific type. So why do they need to do this form? Why can't they just do what Kotlin does, which is obviously better, and do something like smart casting? One reason is that they need consistency with another language feature that I'm going to talk about in a second. But there's actually a second reason, which is even more important, that also prevents them from doing this. So this would be like the old format that you'd write in today's Java. And if we have methods that, if we have a method that's overloaded, so you have one that takes an object and one that takes a number, say for like analytics or something, and then I call this method with that object today. Now imagine Java suddenly enabled Smartcast. When I recompile, what's going to happen is this O local has changed from being an object to an integer, and now matches a more specific version of a method, which potentially has different implementations, and then would change my program's behavior. Just by recompiling, it would change the program's behavior. Now, obviously, like having overloads that have different behavior, like the code itself is already questionable, but Java doesn't do things like this on principle, and so they're not going to change program behavior, and so they can't do smart casting. So that's one of the reasons why they are essentially forced you to introduce a new name for the new typed thing. And also, from doing this, it obviously prevents this behavior change, because now it's a totally new value. Okay, one of the reasons that Kotlin is able to do Smartcast, though, is it had that from 1.0. There's no like 10 years of code that they had to worry about potentially breaking. So in this case, in this direct comparison of language features, I think they get the advantage, because the ergonomics of using this in Kotlin is much nicer. So given one of these value-based classes that we had before, by virtue of using the data modifier, that allows us to use something called destruction, or to destructure this type. And so given an instance of our person, we can extract the individual components back into local properties if we need to. Now, usually, like, this person would be the return value from a method call or property or whatever. So, I mean, this example is a little ridiculous, just creating it and destructuring it, but shows you how the feature works. And this feature is available actually not just for creating local properties. You can do this in the for each style loop. So if you have a list of people or you have a map and you want to extract the keys and values. Or you can use this on lambda arguments. So if you have like a person being passed into a lambda and you're going to use the individual components, you can just destructure them in the argument signature so that you can use the properties directly. All of these are implemented the same way, so we're just going to focus on this first one. And I want to look at the bytecode as to what happens when you deconstruct. And so what happens is it just turns into two method calls. Turns into two method calls, and if you remember from before, I said how when I showed the person class, I omitted the component 1 and component 2. But that's what's being called here. We're calling these methods which return, the first one returns the string because that's associated with the name. The second one returns an I, which is the bytecode representation for integer. And so the full version of the person class, although I guess I'm still omitting the copy methods, has these component functions, and they have the same signature as getName and getAge, except in like a known naming scheme that the compiler can always call. Reason this is worth mentioning, and I certainly think it's interesting, is that these methods are part of the public API of this class. And so if I'm evolving my application and I want to add another property to a person like nickname, I'm adding it here in the middle of the properties. And what's going to happen is if I have that destructuring code in the same module, the age is actually just going to turn into the nickname. Because these things are not, they're not like nominal, which means they're not name-based, they're positional. And so because I'm just destructuring, two items, you just get the first two. But if this destructuring code is in a library and the person class is in some other library that my library consumes, and I don't recompile my library, you actually get a no such method error at runtime. And this happens because when I add that property in the middle, it changes the signature of the component2 method, changes the return type. And so code that was calling component2 and expecting an integer will fail to link at runtime. Like it won't find the method that returns integer because now there's only the one that returns string. I want to compare this to what happens in Java. Now, right now, there's no syntax proposal for destructuring in Java, at least not from like a known type. So I say known type because like in this case, like we're creating Alice as a person, and we know she's a person, and the compiler knows she's a person, so we're able to just call like .name or .age or call the methods .name or .age in Java because it's that type we know. But in the last section, I talked about how we could do a type test and define like a new local variable for things that we don't know. And so this syntax where we have an object that might be a person and we type test it's a person is also going to be augmented to support deconstruction. So if the type test succeeds, what's going to happen is the name and age local variables will be made available in the scope of the if statement here. The Java language is basically, in its implementation of this feature, it's asserting that deconstruction or destruction is only really going to be useful, or perhaps that it's like most used with a type test, where you're getting something of a certain type, you want to test that it's a different type, and then perform deconstruction. And so it's like consolidating these features together under the assumption that they'll mostly be used together. For Kotlin, these are totally separate concepts. If we have an any that might be a person, the type test is totally separate from the destruction, which we can then do because of smart-casting. If we look at what happens here in bytecode, so I pointed out the example in bytecode for Kotlin. If we look at how destructuring is implemented in the Java bytecode, we get this crazy thing. That yellow part is the method name. It looks crazy. What they're essentially doing is encoding the types that you can deconstruct into the method name. And there's a reason for that, which we'll get to in a second. But then what happens is when this method is called, it actually returns, it's like a factory for pattern matchers. And so you call this method, and it gives you back something which can do the type test, and then knows how to extract the name and age. All right, going back here, if we do the same trick where we want to evolve our person class and add a new property in the middle, what happens in the bytecode? Well, that method is going to change its signature. And so we have the same problem that we have in Kotlin, where old code that was compiled against our person class is not going to be able to find the method in red there. Instead, there's only going to be the method in green. However, in the same way that you can do things, so like I didn't mention this, but if anyone was calling the constructor of these data classes or records, they would also be broken because we added an argument. Now, both languages are going to allow you to introduce a second constructor that allows them to be binary, like compatible with those old callers. There's no syntax for this in Java. This is the only example that I've just 100% made up myself. But they have declared that they're going to allow you to overload these destructors in some way. Some syntactical way you'll be able to define a secondary destructor. And so given my made up syntax here, what will happen in theory in the bytecode is that because I added the second constructor and I added the second destructor, when I add that new property, all that happens is new things are added to the class. Nothing is actually removed. And so this then becomes binary compatible with old callers. Another cool feature of so in Java, this is called, this language feature is called pattern matching. It's not actually just destruction because it's associated with the type test. And so another cool feature is that this starts to interact with other language features that we've already talked about. So if I go back to where I was using those sealed types, and I change, I have these locals, instead of object, I switch to developer. So I'm now using the base type of this sealed hierarchy, where a thing is either, an instance of developer is either a person or it's a business. If I want to match on this now and ensure that I'm exhaustively matching, in Kotlin, we use the when construct, and we don't have to put a default case or an else case because the sealed type, Kotlin knows it's a sealed type, and it knows we've covered all the cases. And then we also still get smart casting because we've done the type test. If we look at the associated Java, they're actually going to in bringing pattern matching to conditionals, it's also going to be brought to switch statements. And so we can do the very same thing, but now because we can also bring along that destructuring feature in the case block. And I also want to point out, I'm using a format of the switch statement here where it almost looks like a lambda. Where you can just put a single expression to the right-hand side, something we can do in Kotlin as well. This is actually in preview in Java 13, the current version, and is proposed to be standard in Java 14, which comes out in March. And so even though this is the same as the instance of version of this that we did before, because this is changing the switch feature, you won't actually be able to use this version where you just do the type test and define a new name for that type. That's going to come to if statements first, and it won't come to switch statements until they add pattern matching as well. But here again, we see our ability to destructure person. What's nice is that these scope themselves, these local variables that we're introducing, scope themselves to just the individual case block. If you're familiar with using switches in Java, the switch itself is a block, but case statements aren't normally their own block. And so if you define a local in one case, say is variable A, and then in another another case block, you want to define another variable a. Those are actually considered in the same scope and will clash with each other. But this feature, they sort of like, because they're introducing a new place to define locals, they can get around that unfortunate limitation that they've always had. OK, I want to change keep evolving our model here and make it a little more rich, where I now have two sealed hierarchies, and one is referencing the other. So in this case, like for our downloads, you can either download an app or a movie, like say we're building iTunes or whatever. And an app has a developer, which is either a person or business, and a movie has a director, which is always a person. Now, if you have an instance of a download and you want to start like querying things like its types and its values, let's say we want to find we have our Alice person. I want to find everything that Alice has done. So she's either made some apps or she maybe has directed some movies. And so I can check if the download that I have is, like say I'm doing this in a loop or whatever, a filter. I can check that the download is an app. I can check that the developer is a person. And then I can check that that developer is Alice. And then if it's not an app, it's going to be a movie. And then I can check to see if it's directed by Alice. And then we can print out this is the movie for Alice. And then otherwise we say like this is not by our friend Alice. So this is like OK in Kotlin, and you see there's like great use of Smartcast, but we lose exhaustiveness checks. And then if I add a TV show, we lose out on like our code is still going to compile, and we're not going to find any TV shows in which Alice was the showrunner. So to do this, you would usually switch to like a when. And unfortunately, with a when, though, we have to start like nesting, and it becomes harder to pull these things out. The fallback case, the not by Alice case, ends up getting duplicated. And it just turns into like quite a lot of code here. And if we want to use destructuring, like you don't really need to follow along with what's going on here. I'm just sort of like picking on Kotlin a little bit here, where these language features that are supposed to be helping us with sealed types and destructuring winds up producing a little bit more code than we might be comfortable with. And the reason I chose this example is because if we try and do this in Java, because they've coupled these things together, type tests and destructuring, it actually turns out to be like really pleasant. And so in Java 14, which is coming out in March, you'll be able to do this, which is they're changing switch to be an expression, something we're familiar with in Kotlin. But then with the pattern matching feature that's coming in the future, we can start doing really clever things. So we can do the thing where we destructure app, but we really only care when this developer is a person and only when that person is Alice. And so what the syntax allows us to do is replace that variable with another pattern, where we only care about a person, we only care about Alice, and then if you remember, like Java stole back the underscore. You used to be able to use underscore as a name. They stole this back because they want to use it for pattern matching as like a wildcard where nothing matches. And so we don't care like what age Alice is. All we care is that the person is named Alice. And so that first case statement will then match on any apps by Alice. And then we can do the same trick for movies. But we have a problem here, right? Like we haven't exhaustively covered all instances that this could match. And so we need a default case. But if we use default and we add a new type, we're not going to be forced to update this switch statement. We're still going to miss out on TV shows by Alice. And so what we can do is actually, instead of a default case, we can just complete the exhaustiveness checking, where we can say any other app or any other movie. We don't care what's inside of it. We know that's not by Alice. And so in terms of like who wins here, it's just like I think it's clear that the Java is like less code and a little more readable, but This example was specifically chosen just to like make the Java example look good. And if you'll remember, like other things like pattern matching like the type test where you get Smartcast is like dramatically better in Kotlin than it is in Java if that's all that you're doing. Okay. I want to end really quickly on touching on coroutines. Coroutines are a language feature in Kotlin where it's like this amazing paradigm shift in how you program asynchronously or concurrently, and so I can write things that like launch 10 coroutines, which each delay from 100 to 1,000 milliseconds, and then like print their value, and it's really easy to do. Doesn't start up any new threads. Like all this actually happens just on the main thread. Even though we're launching these 10 coroutines, they're all like scheduled in one thread and are delayed. IntelliJ shows you these like cool things for it. And Java is getting a feature like coroutines, but it's not a language feature, so I didn't really want to highlight it. What's happening is they're just taking blocking methods and turning them into being asynchronous. So if you call thread.sleep, it's just going to like unhook your method, your call stack from the current thread, and then like mount someone else on top of it to allow them to continue running until that thread sleep is done, in which case it'll like do the opposite thing, and your like virtual thread will come back on and start running again. This is something that's like really new and coming. Probably this is like the Java 19 of the talk, where it probably won't be 3 years until this is available. But it's something to keep in mind because you don't have to update any code. All your blocking code suddenly becomes like essentially suspendable. Okay, so is this are these language features of Java the end of Kotlin? It seems like Java is really playing quick catch-up here. All the things that we take for granted in Kotlin will be available to our Java developers in 3 years, and will we be able to incentivize them to still switch to Java and switch to Kotlin and still convince them that Kotlin is something worth having? And so while these things are coming to Java, I think the answer to this is like a resounding no, that it's not the end of Kotlin, and yes, that we still will be able to incentivize them to switch. New improvements in APIs and the virtual machine help Kotlin. All the changes in bytecodes and stuff will be available to use by Kotlin C. So as Java is evolving, Kotlin is also evolving. One thing I didn't mention, like sort of the elephant in Java's proverbial room, is nullability. That's one of the huge benefits of Kotlin, of having nullability modeled in the type system, and they are not planning to tackle that to the same degree as Kotlin has. And then, I'm comparing Kotlin today to Java in 3 years, not Java in 3 years to Kotlin in 3 years. Kotlin, hopefully, in 3 years, will also be evolving and get a bunch of new shiny features. And then a really cool thing is, Kotlin has the IDE to allow it to progressively migrate code bases forward to have new features, and that's something that Java cannot do. And then, obviously, multi-platform is a huge endeavor, obviously being pushed, and it's something that's, really starting to prove itself as being viable. And while Java has the ability to do multi-platform through third-party things, it's not a first-party supported solution. And so, to answer this question is, in 3 years, is like this going to be the end of, the Kotlin language feature or Kotlin language, and we're all going to switch back to Java? I don't think so. Thank you all for attending.